Welcome to our presentation today. We're going to talk about MTIA, which is Meta's in-house training and inference accelerator. We'll talk about how we've co-designed our models to give us high efficiency for inference workloads in the data center. I'm Joel Coburn, along with my colleagues Junqiang Lan and Jack Montgomery, and we're going to take you through the model co-design process on MTIA. I'll briefly talk about model co-design. Junqiang will jump in and talk about silicon architecture, how we've customized it for our models. Jack will talk about the software stack and the developer ecosystem. And then I'll wrap up by talking about some end-to-end results and future directions for our accelerator program. So now let's jump into model co-design. I want to start by taking a look back at last year's Scale Talk, where we introduced MTIA and talked about these three pillars of a successful accelerator program. First, we focused on the end result. So the goal with MTIA was to improve user experience for applications like Facebook, WhatsApp, Instagram. And we do that by providing more accurate, interesting predictions, increasing watch times, click-through rate, etc. And that all comes down to our ML models. And using MTIA, we can provide better developer efficiency and better perf per TCO to deploy them in the data center. So on the developer ecosystem side, we've created full PyTorch support for MTIA to provide a familiar developer experience. And we'll talk more about that later, as well as Triton support for kernels. And all this helps to solve the programmability challenge in any accelerator. Then we've also focused on the design process so that we can design the chip and the system to give us the best perf per TCO, but then also we could minimize the time to market so we could get to market quickly, because the competitive landscape is very difficult for accelerators. And we did this by leveraging open source components, vendor partnerships, leveraging third-party IP, and then we could focus on designing the custom logic for the key parts of our models where we could get higher efficiency. So with that in mind, let's look at some model trends now that are really driving adoption of MTIA. So we focused on the ranking and recommendation space. And particularly in late-stage ranking, we've seen an increase in model complexity and model size over time. The graph on the upper right shows that as we increase the gigaflops per sample, we continue to improve the accuracy of predictions with the model. So that means there's still value to scaling up the model. At the same time, we have this challenge where we have a really broad set of applications and a huge range of models to serve them, as much as 60x gap in complexity and size. We also are seeing a lot of accelerator demand for early stage ranking. This is where we do retrieval and ranking of a large number of candidates for the late stage, and the models tend to be very low complexity and high throughput. And then finally, we see a trend toward Gen AI techniques for recommendation models. So this is even more demand. So sequence-based models with transformer-like architectures can provide better prediction quality here. For example, the HSDU architecture at Meta does this, but it has over 10x increase in complexity and model size compared to our state-of-the-art late-stage ranking. So now let's look at the silicon and the system and choices we made to co-design it for our models. So on the silicon side, one key choice was to build the chip with a very large SRAM cache for holding activations and caching embeddings. This makes our models much more efficient. It also was a key decision because it allowed us to also pick LPDDR for off-chip DRAM as opposed to HBM, which many accelerators have today. And it turns out we don't need it here because we don't need as much off-chip memory bandwidth. LPDDR is lower power, it saves us money, but interestingly, we have to deal with doing ECC inline, which costs us some performance, but it is a worthwhile trade-off here. We've also built several offload engines in the hardware to accelerate sort of the most expensive operators in our models. So dot product engine for gems and SIMD units for activation functions and embedding pooling. We've also explored numerics and model compression by supporting types like FP16, int8, int4 that are particularly prevalent in our ranking and recommendation models. Another thing we've been able to do is really customize the ratio of flops to memory bandwidth, to memory capacity, and to I/O bandwidth with the host. And that's something that's much more difficult to do in a third-party solution. And then finally, with our knowledge of the serving stack, we've been able to optimize the system design so that we really get the right balance of partitioning models between CPUs and accelerators. And that's led to a much denser system design. We have 24 ASICs connected over PCIe and a dual socket CPU. And this gives us much higher perf per dollar and perf per watt. So now let's consider the PyTorch ecosystem and what that means for MTIA. So we've provided PyTorch to give us a familiar developer experience, all of the features that developers are used to. And we've adopted it also to support PyTorch 2.0, where we can get things like Torch Inductor and Torch Dynamo to basically support the demands of new models and efficiently map our operators to MTIA and to other backends. And then finally, on the kernel authoring side, we've added support for Triton. So you can write the same kernel that can run on a GPU, CPU, or an accelerator like MTIA. And Jack will discuss all of this later. So finally, I'd like to share a comparison between MTIA v1 and MTIA v2. Compared to the chip we announced last year, our v2 design is much more powerful. And this was one of our main goals. We wanted to be able to have it be more capable to serve even larger models to improve our applications. So a few things I'd highlight. We have 2x more on-chip SRAM, which improves our performance. We doubled the LPDDR off-chip to serve larger models. We've increased the on-chip SRAM bandwidth by 3x, and we've done that really to feed 3x more peak flops, which allows us to serve those more complex models. The v2 design is very competitive in terms of absolute performance at a rack level with our baseline deployed in the data center, and it's capable of handling these larger models with significant perf per dollar savings. So now let's dive into the silicon architecture, which Junqiang will talk about.
Thanks, Joe, for the introduction. I'm going to switch to the MTIA accelerator itself. Hi, everyone. My name is Junqiang Lan. I'm an architecture lead from the infra-silicon team of Meta. AI and its applications can significantly change the world and our lives. The active triangle of ML model, data, and computing resources are the three main driving forces of the AI wave today. It is our great pleasure to contribute from the computing side and share the updates on MTIA silicon development. MTIA stands for Meta Training and Inference Accelerator. It is a customized designed processor for Meta AI models and workload. The overall better power efficiency or perf per watt as target in mind, the so-called next generation accelerator is a continuation of the previous generation we unveiled last year. In my section, I will give an overview of the chip, then explore the architecture a little bit. Then I will focus on the unique optimizations specifically for our own model and applications. Lastly, I will share the future direction of the MTIA program. The next generation accelerator has been landed in our data centers and started serving real traffic. The chip was taped out with TSMC 5nm process. The plan on record targeting frequency was 1.1 gigahertz. But with the margins from solid backend timing closure and also thorough characterization from the lab, we were able to boost it to 1.35 gigahertz, which gives us 20+% performance boost. It is a complicated ASIC with 2.35 billion gates on the die, but as you can see, the silicon in my hand. In the world of AI accelerators, this is already a moderate-sized chip with total power of 90 watts. Let's take a closer look at the architecture of this generation. You can see we have the same 8x8 compute grid as the previous generation with more balanced NOC or mesh networks. Each PE again consists of CPU control cores, dedicated matrix multiplication engines, and special math engines. We also support SIMD or DSP-like vector extensions for generic programming. We made significant improvement on the computing, which is the key metric for AI acceleration. We achieved 177 teraflops on FP16 and BF16, which is 3.5x over the previous generation. On the integer support side, int8 and int4 are 2 times, 4 times the number as the floating 16-bit. On the memory hierarchical, we increased on-chip SRAM, increased DRAM size, we increased the bandwidth to just have a more balanced computing and memory. Besides the power and TCO or total cost ownership benefits, the reason that we are going with in-house design is to have a better vertical integration all the way from our model to accelerator hardware design. Here are a few examples. We achieved higher computing, as we mentioned in previous slides. We supported sparse matrix multiplication and yield more effective T-flops by ignoring the zeros. The weight is further compressed by asymmetric number system or ANS algorithm. This saves bandwidth and also have better power performance. We also optimize the mesh network so that the compute and data movement are more balanced. And the three detailed optimization I'm going to dig a little bit deep is for small precision integer inter-8 quantization, dynamic quantization support, PyTorch eager mode, and also the table batch embedding optimization. Let's dive on these optimizations one by one. Quantization is common to convert data to lower bits precision for fast or efficient gen in the next layer. The exact dynamic range of data is collected in MTIA post-gen, and the quantization parameter is most accurate compared to static quantization. Channel-wise dynamic quantization is built in. So this brought us a less than 0.05 loss or normalized entropy difference to compare with the 32-bit floating point numbers with very high accuracy. PyTorch eager mode requires immediate execution. Direct way of host to launch a job is to do a command copy, interrupt to PE through IPC. P and CPU reads the job descriptor. The interaction between CPUs brought long latency. In this generation, special hardware's blocks are added to broadcast working queue to PE. PE then use DMA to read the descriptor so that the CPU is offloaded. This brought the whole job launch time to 20%, only 20% with previous generation. Table batch embedding is one of the most important optimization on inference in ranking models. As MRS, we specifically built hardware features to accelerate TBE. We added new hardware instructions. We support rotate DMAs. Multiple contexts unrolling is also supported. We also add the compression engine to alleviate large embedding indexes to load from host to the P side. We achieved 2 to 3 times faster than previous generation on TBE operations, and we also achieved 30%, up to 30% SRAM flying bandwidth. Successful landing on silicon into production is not an easy goal. It is a multi-year planning, flawless execution, and close interaction among multiple organizations and teams. Great thanks and big applause to all the cross-functional teams to make it happen. The chip is now running real workloads with a better perf per TCO. This journey is 1% done. We're looking into some of the most exciting improvements as listed on the slides, including the obvious more computing, higher efficiency, multi-device collaboration via collectives, Gen AI, large language model specific optimizations, as well as more meta-only workload support. Please stay tuned for more silicon updates down the road. Next, I will pass to Jack to talk about software optimization on MTIA. Thank you.
Thanks. My name is Jack Montgomery, and I'm going to talk about what we've been working on in the MTIA software stack. In this section, I'll share 5 main ideas about MTIA software. First, the principles and goals of the software stack, PyTorch integration, kernel authoring with Triton, support for new features and model types, and finally, scaling model performance. Firstly, a set of core principles guide the development of the MTIA software stack. These include being PyTorch native, which we'll describe in more detail shortly, achieving both high performance as well as high developer efficiency, balancing the hardware heterogeneity requirements of our AI systems with the requirement of leveraging the unique advantages of MTIA hardware, building everything in a simple and composable way so that it can change and adapt quickly, as well as supporting scaling the system across many different axes, including number of devices, types of models, number of models, model sizes, etc. Now we can talk about PyTorch runtime integration. Engineers familiar with using GPUs in PyTorch feel right at home with MTIA devices because of the native PyTorch integration that MTIA software has. MTIA is a first-class PyTorch device, which means that you can use it just like you would use CPU or CUDA devices in PyTorch. There are MTIA device tensors, just like CUDA device tensors, for example. Additionally, libraries that are built on top of PyTorch can add support for MTIA with very little effort. It supports eager mode and graph mode execution, which are the two main execution modes in PyTorch. Eager mode means you can run one operator one right after another on the device without any changes to your model. Graph mode means that you can precompile, fuse, and optimize large chunks of the model together for maximum performance. It's also possible to mix and match these two different execution modes for maximum flexibility. On the right side here, we have a code snippet showing how easy it is to run your model using PyTorch and eager mode on MTIA devices. It will look familiar to anyone who's used to using PyTorch. Direct integration with PyTorch 2.0 allows model owners to achieve peak performance on MTIA hardware with very minimal effort. This includes graph capture using Torch Dynamo and Torch Export, and a backend optimizing compiler integration using Inductor. This also will provide out-of-the-box support for thousands of PyTorch operators in both eager mode and graph mode on MTIA devices. We're also able to leverage all of the latest technologies in the rapidly evolving PyTorch 2.0 compiler stack to achieve peak performance on new model types, as well as make models that are already running on MTIA hardware faster automatically. Another exciting thing that we've been working on is Triton language integration. Complex kernels can be written succinctly in the Triton language and run efficiently on MTIA devices. Triton allows users to efficiently write fused kernels for MTIA devices. Also, any existing Triton kernels that run on other device types can be easily ported to run on MTIA hardware. MTIA supports inductor-generated fused Triton kernels as well. These modes of integration can also be blended together as well, which means users can handwrite some kernels on Triton and also allow the compiler to auto-generate other kernels for maximum performance across the entire model. Now let's talk about the fact that MTIA supports key features that are required by the AI systems that it powers. Some examples of this include real-time model updates, which allow our AI systems to learn and adapt quickly to new information. It also includes dynamic shape support, which allows the input types to models to change over time, which makes deploying models even more flexible. Sequence models are at the heart of a lot of the latest model technology innovations, and we have a lot of support for these built in order to get maximum performance across a wide variety of sequence models out of the box. Investments in great tooling allow engineers to peer into the MTIA hardware to diagnose and fix issues very quickly. MTIA Insight is one such tool. It gives full, detailed information about the MTIA hardware to engineers who are using it. We also have model, operator, and instruction level tracing to get detailed information about what the hardware is doing at any moment in time. There's also kernel debug support, which allows engineers to look at what kernels are doing when they're running on the devices. Finally, we have numerical analysis tooling, which helps analyze when a model is giving incorrect results and root cause the issue. Now let's discuss model enablement. The MTIA software stack has been put to the test across a wide range of model types and applications. Some of these applications include advanced late-stage ranking techniques, very efficient early-stage ranking, several different Gen AI use cases, as well as content understanding models. Finally, looking towards the future, we're focusing on ensuring that new models can automatically achieve full performance on MTIA hardware out of the box. This includes building generic model compiler optimizations that will work across many different model types, building out a self-service model optimization platform so that users can immediately get maximum performance on MTIA hardware using their models, and also building auto-tuning functionality, which enables the system to configure itself to achieve roofline performance on the hardware without any manual effort. That wraps up what we've been working on MTIA software. Now I'll hand it back to Joel for some closing thoughts.
Thanks, Jack. Now I want to go into results and future directions for the MTIA program. Let's start by looking at some model co-design examples that really tie together the software ecosystem and the silicon design. So let's look at a few different areas here. We focused on kernel optimizations for one, where we really tried to optimize kernels to take advantage of our offload engines and our memory hierarchy. Specifically, we focused on large gems because they're an important part of scaling up ranking and recommendation models. So if you take a look at the picture in the upper right, this is a diagram of a gem implementation that tiles the weights from DRAM into SRAM so that we can feed the dot product engines directly out of SRAM with that high bandwidth. Another thing we did in the gem space was actually create in software an auto-tuning framework so we could automatically generate different gem kernel variants for specific shapes optimized for our architecture. We also spent a lot of effort on the compiler side. We worked on graph transformations to generate the most efficient patterns for our architecture. So we, of course, did things like operator fusions. You can see in the picture on the bottom right, we were able to fuse, in this example, a transpose with 3 FCs in parallel that consume its output. And because they share that input, we're able to run them together and only read the input once. We've also been able to eliminate a lot of unnecessary data movement operators, and we've been able to provide custom tensor placement and graph scheduling, which you know can make a really big difference in terms of SRAM locality. Finally, I'll talk just a bit about the host serving stack, because we did a lot of optimizations there to be able to efficiently shard models across multiple cards, utilizing peer-to-peer over PCIe, and to be able to stack multiple model instances across cards so we could have a fully loaded system in production to get the most utilization out of it. So now let's look at some end-to-end results on MTIA to see where we stand. So we evaluated MTIA against our baseline deployment in the data center. And we evaluated it against a set of late-stage ranking models, some low complexity as low as 7 million flops per example, and some high complexity as demanding as 680 million flops per example. You can see in the graph on the upper right, we plot our performance improvements over a 7-month period of time. This is absolute performance at a rack level compared to our baseline. And in terms of capability, they're about the same in terms of peak flops. So it's a pretty equal comparison. And you can see that performance improved over time, but particularly as we onboarded new models, the time to optimize a new model went down. So our developer efficiency was improved. Now let's look at the graph in the bottom right. So you can see that we get equal or greater performance at the rack level compared to our baseline. And if you look at lower complexity models, sort of out of the box, we have an advantage because we can utilize that on-chip SRAM that we built intentionally for that purpose. You can see on the high complexity model space, we need to do more optimizations to get good performance. So like I talked about, we need to block those gems in SRAM. We need to do more operator fusions to keep all that data on chip, and that'll get us higher flops. In terms of perf per watt, we're equal or better than our baseline, and all except for the most complex model, where there's some ongoing optimization work, and we believe that should be at parity. And then in terms of model flops utilization, the low complexity models exceed the baseline. The high complexity models are still behind, but there's a lot of perf headroom here, and so we'll spend a lot more effort optimizing this in the future. So now that we've seen some results, let's look at some of the opportunities for MTIA going forward. The graph on the right shows that there are different architectural requirements depending on the class of workload. And the class of workloads also changes over time. So when we first were designing MTIA, we focused on recommendation and ranking models, but now we're also focusing on Gen AI. And you can see that there are different compute, different memory, different network requirements across training versus inference, and across recommendation versus Gen AI models. So we must really balance kind of the specialization for these different domains across, sort of the maintainability and the effort of doing those designs, so it's something we can deploy and maintain in practice. The other thing to consider here is that we're seeing a great increase in scale of models, particularly in Gen AI domain. So we really have to focus on efficiency because power is going to ultimately determine what we can deploy. And then finally, like we've talked about, the developer experience is so important here. And so we really need to be able to move at the speed of model innovations. And so that'll mean keeping up with, the pace of PyTorch changes and being able to keep up with the latest, most exciting models. So we're really looking forward to the future of MTIA, and we appreciate your time. Thank you very much.